Dr. Sosi Lorinci, Dr. Eulalia Noanart, Dr. Michael Reckner, Dr. Laura Sakerdo. Thanks for the invitation. Okay. Since 1990, among others, I keep busy with fractional calculus. Fractional calculus is a very old subject, as you know, from 1695, 326 years now. And till 50 years ago, it was not so popular, as you know, because of these complications, complicated formulas, etc., etc. But in the last 50 years, they discovered a lot of applications of fractional calculus, and so more and more people are using fractional calculus in various subjects. Main streams of fractional calculus is itself, in other words, dealing with new definitions of fractional derivatives, integrals, etc., etc. Then the fractional differential equations, univariate and multivariate, and applications in physics, economics, etc. Myself, I started applying fractional calculus in the area of inequalities, and I still do that. And also, from 1990, my effort was to involve fractional calculus in approximation theory. And there I have not seen anybody working in recent years. Very, very long ago, 1960, I had seen some papers from the ex-Soviet Union. So it's highly possible I'm the only guy working in fractional calculus and approximation theory. In inequalities, there are a lot of people working. Okay, this topic of fractional monotone approximation is a classical approximation theory topic. Starting in 1965 with Ovid Sisa, who was a mentor of mine and was the founder of the Journal of Approximation Theory. He, of course, now he's dead, unfortunately. So in 1965, published an article in Pacific Journal of Mathematics, the following: if you have a function whose k derivative is greater or equal to 0, find polynomials with the same property approximating simultaneously this function. So the polynomial must have the same property. In other words, preservation of monotonicity or preservation of convexity. Okay, that was 1965. In 1985, in the spring, I was at the University of Rhode Island starting my career after my PhD. And Ovid Sisa had an open problem: how to replace the derivative with a linear differential operator of order k. Where I spent all the semester, I gave the solution, very lengthy, but Ovid shortened it and had a publication together in the Journal of Approximation Theory of that year. Okay. Then I try, okay, let me show you the theorem of that time. Let h, k, p integers in that order 0 to p, and f real function with a p continuous derivative and modulus of continuity. You know, modulus of continuity measures the smoothness of a function, and the speed of convergence is a primary tool in approximation theory. Let Aj, the coefficients of linear differential operator, all defined and bounded on -1, 1. In approximation theory, the interval -1, 1 is very typical. Is like any interval AB, you know, it's typical to use -1, 1. And AH, the first coefficient, is bounded away of 0. That's the assumption. You cannot do it without that assumption. And consider L, the differential operator, and assume L of applied on F is greater or equal 0 pointwise on -1, 1. Then find polynomial Qn with the same property, LQn greater or equal 0, and converging uniformly to F. And you have this nice inequality. Okay, that was the beginning. Over the years, I have generalized more and more this theorem in 2 dimensions, also in fractional cases. I mean, using fractional linear differential operator of Caputo type fractional derivatives. And the benefit using fractional linear differential operator is that the assumption is weaker than, as you will see, as using ordinary linear differential operator. Okay, let me define the space of approximates because I'm working in 2 dimensions. 2-dimensional problem is harder than 1-dimensional. So I thought to give more insight of what's going on here. So let NM integers, P theta denotes the space of algebraic polynomials degree less equal theta. And you have the tensor product spaces Pn, C -1, 1, C -1, Pn. So a pseudo-polynomial is combination of polynomial and functions in 2 dimensions, functions continuous. This space was introduced by Marceau, 1924-27. Okay, this dk plus L theta dxk d theta dy L is the usual ordinary KL partial derivative. Okay, the measure of smoothness we use here is, of course, bivariate. It is based on the mixed difference of order Sk. This double summation and this, take the soup of all this, is a measure of smoothness, converges to 0 as the deltas converge to 0, etc., etc. So that's the modulus of continuity we are going to use now. Okay. Well, because I want to save time, this is a theorem of Gonska of 1985 regarding ordinary approximation of functions by pseudo-polynomials. Is a pointwise result from which I derived this corollary, which I'm going to use in my work here. Let me go over that carefully. Let RP integers, SQ natural numbers, F in CRP -1, 1 square. CRP means you have per coordinate continuous derivatives up to order R in the first coordinate, second coordinate up to order P. Let NM natural numbers greater than certain numbers. We don't care for the first natural numbers, we care for the bigger ones because we are talking about convergence. So definitely there are infinitely many, almost all natural numbers above these lower bounds. So there exists pseudo-polynomial QNM approximating simultaneously the function f, where KL is between 0, 0 and RB. That means 0 less than K less than R, 0 less than L less than P. Okay, and I write it in pairs for convenience. The constant C hat depends only on R, P, S, Q, not on F, not on N, not on M. That's a typical approximation theory given with rates, with inequalities. Okay. Let's see. Am I right? Okay, I'm doing okay. Okay, 1 second. Let me maximize a little bit. So, well, now I have your pictures here. Okay. All right. Okay, that's the theorem of 1991. I proved using pseudo-polynomials, still not yet fractional. Let H1, H2, V1, V2 are P integers with these orders from 0 to R, from 0 to P, F in CRP, FRP having a mixed modulus of smoothness. Usually we would say smoothness for higher order or two-dimensional. And Aij, again, real valued and bounded functions of -1, 1 square. And the first coefficient always will be bounded away of 0 in this paper. Cannot be without it. Okay, and assume L of F greater or equal 0. Then for N and M greater than certain lower bounds, there exists polynomial Qn with the property LQn greater or equal 0. That's the monotonicity achievement here. L of F is greater than 0. L of Qn greater or equal 0. Okay. And the convergence is simultaneous. Simultaneous approximation. And I distinguish different cases of the indices, and I give different type of inequalities for each case. If KL is between 0 and H1, H2, I mean the orders of differentiation, then you have this inequality. If are here KL, H1 plus 1, H2 plus 1 to RP, then I have this inequality. Also, this 14 is valid when 0K H1 order and H2 plus 1 LP order, or in the other case, H1 plus 1 KR order or 0 LH2. So it depends the KL in what position are with respect to other indices, H and RP, H1, H2, and RP. The constant C is independent of F and M. It depends only on RP, SQ, L, and the operator L. Okay. Let me now, a second. Now I use a definition by Samko and Mamatov. The Riemann-Liouville integral left side. By the way, I have created also a right side theory, not presented here, but similar paper. So all these will be published in a short monograph in April by Springer. And this is what is expected, left mixed Riemann-Liouville fractional integral in 2 dimensions of order alpha. Alpha is a alpha 1, alpha 2, a pair of orders. Okay. Okay, 1 second. Now, based on this integral, I define the Caputo type corresponding bivariate fractional partial derivatives. See number 16. This is what is expected, right? Gamma, the gamma function, and I have special cases. If alpha 1 is 0, univariate integral. If alpha 2 is 0, univariate integral. All these are expected and known in the literature. Okay? So based on this, in I think it was 2015, I replaced L by L star, a linear left Caputo fractional mixed partial differential operators. And now the metonicity will be true of the critical square 0,1 square for the left side approximation. For the right side approximation is valid in -1 square, -1 0 square. Okay? Simultaneous fractional convergence remains true on all the square -1 1 square. So here is the theorem, the fractional monotone approximation theorem. Let H1, H2, V1, V2, Rp integers in that order 0H1 R, 0H2 P, F in CRP, and FRP have a mixed modulus of smoothness, omega SQ. They are the coefficients alpha J, defined and bounded on Rp, and suppose the coefficient, the first coefficient, always the first coefficient of the linear differential operator, must be bounded away of 0 in the critical square 0, 1 square. Okay? And then m greater than these lower bounds. Set Lij, the sup on -1, 1 square of the inverse is not functional, is numerical inverse of alpha H1, H2 times Aij, A H1, H2, Aij. So this is numerical inverse. And of course they are finite. Okay. Let the fractional orders alpha 1i, alpha 2j, with ceilings I and j. I from 0 to R, j from 0 to P. Ceiling is the ceiling of the number, is the smallest integer above the number. I set A1, 0, 0, A2, 0, 0. And consider the left fractional bivariate operator here with this bivariate fractional derivatives Cafuto type. And assume that L star F is greater equal 0 on 0, 1 square, on that critical square. Then I'm able to find Qn star pseudo-polynomials with the same property. Okay? Greater equal 0 on 0, 1 square. And also having simultaneous approximation on -1, 1 square. Always we have the main things here is the mixed modulus of smoothness of 1 over n, 1 over m, and then you have here n, r minus I, and p minus j. By the way, when you do constrained approximation, the speed is reduced, is not the Jackson speed of 1930, it would be 1 over n, and 1 over m is multiply 1 over n times 1 over n r minus I, 1 over m times 1 over m p minus j. So you have reduction when you preserve the same. C hat is a constant depending on RPSQ, and I distinguish different cases regarding to the indices where Ij is, and I have similar inequalities produced with precise constants found. I mean, it's complicated. I'm not going to go to details on that. There are about 5 cases regarding the simultaneous approximation. Okay. So what we will do in this article is the following. I'm making an effort in recent years to unify fractional calculus. That's my book just appeared in Springer, trying to unify in action the fractional calculus. So what that means, there are two different schools. One is the traditional school of fractional calculus with singular kernel in the integral and derivative, and the other is the non-singular people. Of course, there are differences. There are things one can do, the other cannot do. Anyway, but there are ways to combine things. One such way is the famous Prabhakar fractional calculus, and also the Caputo-Fabrizio non-singular fractional calculus, and the Saxena-Kala fractional calculus, non-singular calculus. So I'm trying to combine things. Okay, so let's continue to go to the point. Okay. So, as I said, I had done the problem of fractional calculus with a usual bivariate Caputo type fractional derivative. Now I'm trying to extend things, go more abstractly. Here is how I go in my definitions. Let's H1V1R greater or equal 0, H2V2P greater or equal 0, F in CRP, and I between H1V1, J between H2V2. The fractional orders alpha 1I, alpha 2J greater or equal 0, non-integers. The ceilings of alpha 1I is I, the ceiling of alpha 2J is J. I runs from 0, 1, R, J, 0, 1, P. See, I mean, this symbol is the ceiling of the number. And, excuse me, okay, sorry. Okay, all right. I consider also the integral functions K1I, which symbolizes uppercase alpha 1I, K2J symbolizes K2J. They are from 0, 2 to R plus. And I runs from 0, 1 to R, J from 0, 1, P. I'm trying to generalize the kernels. So I consider the abstract left Caputo type bivariate fractional partial derivative of orders alpha 1I, alpha 2J. So this is how I symbolize it. K1I, K2J has to do with the kernels, is Caputo type, left type, of course, of the orders alpha 1I, alpha 2J. And I have here the abstract kernels. So it's following this Caputo way. In fact, it's Louisville way long time ago. Most recently, it's called Caputo. The partial fractional derivatives in trivial cases, etc., etc. Okay, what is very important here is this assumption. I need you, please, I call it 40. I need you remember that because the paper is based on that. That's where it's based. Integral from 0 to 1, K I H I Z D Z greater or equal 0. When H I is different than 0, I make this assumption, which for I1 to which is true if you go with the ordinary kernels. If you use the ordinary kernels of left Caputo type fractional calculus, this KIHI is this thing, what you see here, and fulfills number 40. One more time, this integral has to be greater than 0, and is fulfilled in the well-known case of Caputo bivariate fractional calculus. Okay, let's present some fractional calculi, unifying, a little bit complicated, but some are well-known. Well-known and fulfill the number 40 for particular choice of parameters. So, We consider the Prabhakar function, well-known three-parameter Mittag-Leffler fraction. Dr. Mainardi has written a nice book with his colleagues on that topic. Okay, F is in C1, Cn1 and 2 on the rectangle, where mu I are fractional orders. Mu1, mu2 are the fractional orders. The rho, gamma, omega are parameters. So I introduce the bivariate Prabhakar Caputo left partial fractional derivative of order mu1, mu2. This 42, you see here. Okay? It has here the Prabhakar function. Parameter omega 1, parameter omega 2, rho 1, rho 2. Remember the parameters, omega 1, omega 2. And of course, the trivial cases. Okay. Then, one second, we jumped. Okay. Next, we use the multivariate analog of generalized Mittag-Leffler function from the well-known paper of Saxenas and Kalla, 2011. Let lambda gamma rho j, complex numbers, real part rho j positive, and we have this function in m variables, this little monster 44, you see it here. The gamma j k j is a Potsdamer symbol. The work of Srivastava and Daust proves that this is convergent for real part rho j greater than 0, j1 to n. Well, I specialize. I take this function, I use it twice with index theta, take values 1 and 2. Here I have parameters omega. Here I have variable t theta. T theta is going to be t1, t2. So I use that twice, the epsilon. And rho theta, the exponent. Anyway, the rho's are between 0, 1, t theta positive, lambda theta positive. The omegas are different than 0. So I use this structure. And F on C, n1 and 2 minus 1, 1 square. Nu theta are the orders with ceiling nu theta, theta 1 and 2. Well, I define the bivariate Caputo type generalized left fractional partial derivatives with non-singular kernel of orders mu1, mu2. Also, the Prabhakar combines singular and non-singular operator. It's a mix. Here is only non-singular. You see it here. It's a little monster, but what to do? For, number 45. This alpha is a normalizing constant without loss of generality. I can assume it's positive. And I have here this product of the two epsilon functions and with multivariate array here, the parameters, etc. And then another example is the bivariate parameterized Caputo-Fabrizio non-singular kernel left partial fractional derivative of orders mu1, mu2. Is this one here. Again, Caputo type, but this kernel here is not singular. Okay. This fractional calculi I just mentioned, 3 of them, for large enough omega theta, the first one, the Prabhakar, for small enough omega, omegas, the Saxenas and Caputo-Fabrizio, they fulfill number 40, this integral of the kernel greater equal 1. They do. Okay. Now comes the time to present my main theorem. Theorem 10. Let's H1, H2, V1, V2 are P integers, 0 less equal H1, V1 R, 0 H2, V2 R, and let F in C RP minus 1, 1 square, FRP. The mixed has mixed modulus of smoothness omega SQ, delta 1, delta 2 positive, where SQ natural numbers. Alpha I, J, X, Y is the coefficients of the linear differential operator, I H1 to V1, J H2 to V2, defined and bounded on minus 1, 1 square. But the first one, alpha H1, H2, here is the coefficients, 48, is bound away of 0, greater equal alpha positive, less equal beta negative, throughout the critical square 0, 1 square. Again, the right-hand side theory will be minus 1, 0 square. Okay, for n large enough, and Lij, this we set Lij the soup of numerical inverse alpha H1, H2, Aij finite, the soup, and the fractional orders alpha 1i, alpha 2j have ceilings I and j respectively. And we consider the abstract left fractional bivariate linear differential operator 48, what you see here. These are the abstract bivariate fractional derivatives of order alpha 1i, alpha 2j. And assume that L star F is greater or equal 0 or 0, 1 square. Then there exists a pseudo-polynomial degree Qn star Nm with the same property, preserving the so-called monotonicity, the constraint. Denote by lambda 1i, the integral from 0 to 2 k 1i, lambda 2j from 0 to 2 k 2j. From different cases of the indices where ij is located, I have about 5 different simultaneous fractional approximation inequalities. Okay? I'm not going to go into details on these inequalities. They are produced in the process of proving the theorem. Maybe you want to see this one. This one is where F is approximated by Q star. You have this compact form inequality, not so messy, okay? These coefficients, okay? These are the speeds, 1 over n, 1 over m multiplied by these speeds here, 1 over r minus v1, m 1 over m, p minus v2. These exponents are positive, of course. Okay, we cover all the cases. Okay, let's go into the proof. See the main parts of the proof. Okay, according to corollary 3, which I derived from Gonska's theorem, we have this, this inequality 55 is already in corollary 3. This inequality 55, okay? And I'm using that. That's the good thing using Caputo type derivatives. I'm using this thing here. Take the difference of Caputo by fractional derivatives, abstract fractional derivatives. You substitute. Then you have this difference of ordinary partial derivatives. And I use the corollary. So it is based on ordinary fraction, ordinary calculus. And I go down by estimating. And I find this difference of abstract fractional derivatives, 2 dimensions. Smaller equal these integrals and these models of continuity, the constant C star independent of everything, almost everything. So there exists such QN doing this job. And again, to remind you, lambda 1i is from 0 to k1i, lambda 2j is from 0 to k2j. What I proved so far is this nice inequality 61. It's good to remember this inequality 61 because it's used heavily in this proof. See it here. It's a nice inequality, compact form, from I1 to 0, 1 to R, J 0, 1 to P. Okay? And then I'm going to use that in the proof. First of all, I consider the following constant. That is a constant, what you see here. I call it rho nm. It's a very constructive proof. Okay, 61, and then this constant. Rho nm, C hat, omega SQ. This is a number. All these monsters, 62, is a number, positive number. Now I distinguish 2 cases. The first coefficient of the linear differential operator is greater or equal to alpha greater than 0. So, according to the theory, as in 61, there is a polynomial, pseudo-polynomial Q star nm. So this inequality is valid. That's another 61. Here is what's going on. I'm using a lifting technique. Instead of F, I applied 61 to this F plus rho n m x to h1 over h1 factorial, y h2 over h2 factorial. Okay, that's the trick. So the derivative of this monomial here, the RP derivative, is 0. So on the right-hand side, again you have FRP. Again you have FRP. That's amazing. You know, this is killed. Though it helps in what you are going to see next. So playing with 63, triangle inequality, etc., 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 and estimating, I'm able to prove the difference, the various 5-kind simultaneous fractional approximation inequalities in the statement of the theorem. So I'm not going to go in details to that. I don't have such time. Okay. Okay. 1 second. Ha. Here comes the crucial part. The monotonicity property. How do we do that? Pay attention on 73. We write in a smart way the A inverse H1, H2, L star Q star NM XY. Adding and subtracting quantities, etc., etc., and using this inequality 63 and using L star of F greater or equal 0, I achieve, using also number 40, the integral of abstract kernel is greater or equal 1. I distinguish 4 different cases here, and I managed to prove that L star Q star is greater or equal 0 on the critical square 0, 1 square. Okay? Then comes the second case. assume on 0, 1 square, alpha h1, h2, smaller or equal beta, less than 0. Then let q star h1, q star xy, the pseudo-polynomial, as in 61, applied now. I'm applying a dropping method now. The same messy coefficient rho and m and the monomial xy. Now I use minus, okay, minus. And here is 1 star, it's not 2 stars, it's a typo. And I have the right-hand side again the same. And then using the same techniques, I produce the simultaneous approximation inequalities, and then writing in a similar elegant way the A inverse L star Qn by adding and subtracting and using the 78 I just said. Now you go less equal, L star F is greater or equal 0 by assumption. And again, I meet 4 different cases, and I finally prove L star Q star greater or equal 0. Okay, we are finishing. Conclusion. The theorem 10, who's the main theorem of the paper, generalized theorem 8 of fractional calculus to many fractional calculi, opening new avenues of fractional research activity. The approximated pseudo-polynomial depends on f rho h1, h2, which rho n m depends on c hat, which depends on rho p s q, f n m, lij, lambda 1i, lambda j. In short, q star nm, the pseudo-polynomial, the approximator q star nm, depends on the type of bivariate fractional calculus we use. So, as an example, I can use for sufficiently large omega 1, omega 2, the Prabhakar bivariate fractional calculus. I can take care of such linear differential operator. The theorem is true. Or the other one for omegas sufficiently small, less than 0, I can use the bivariate generalized non-singular fractional calculus. And third, based on the third example I was saying, for small enough omega 1, omega 2 negative, I can use the bivariate parameterized Caputo-Fabrizio non-singular kernel fractional calculus. So what we gain by using fractional calculus is the weaker assumption that the Caputo bivariate derivative basically is greater or equal 0. Because assuming that the bivariate partial derivative, ordinary partial derivative greater or equal 0, is stronger condition. Here we have involved the integral. So if the ordinary fractional derivative in 2 dimensions is greater or equal 0, then the integral is greater or equal 0, but vice versa is not true. So that's the advantage of fractional calculus, and also the great variety of fractional calculi we can use. That is part of unification of fractional calculus I'm trying. Here are the references. Monotone approximation of pseudo-polynomials, 1991. Bivariate monotone approximation proceedings of AMS, 91. Bivariate left fractional pseudo-polynomial in my conference in Ankara, 2015. My recent papers. Then the Anastassiou CISA paper of 85, part of the history. Atagana Baleanu are fractionalists who created non-singular kernel fractional derivative. Then the good paper by Giusti and Tal on practical guy of Prabhakar fractional calculus. Classical approximation theory from my friend Gonska, 1985. The book, Goer for Kilbas, Maynard, Rogozin, with Tagler functions, 2014. Losaya Neto provides a new fractional derivative without singular kernel. Mamato Samkov, Marceau, 1924, Marceau, 27, Polito Tomovsky, 2016. The great paper by Saxena, Kala, Saxena, multivariate analog generalized with Lefler. Shoemaker for the mixed modules of continuity. The seminal paper of Sisa, 1965. And Srivastava Dowd, 1972. Okay, my friends, I finished. Thank you so much for your attention. And if you have any questions, I would like to ask, to hear.
Thank you very much for this historical excursus with so dense number of results. Are there questions, comments? Aran, I see that your hand, Fernandez.
Yes, thank you for this interesting presentation. I have maybe two questions. Can you show, please, your general definition? I think it was around slide number 14. Yes. So here you have these general kernel functions, k1i, k2j. I was just wondering, what is the function space? Like, what sort of function are these k? Are they just integrable, or do they have some other conditions?
Just integrable, nothing else. Very general, just integrable.
Okay. So this is a kind of general convolution operator, we could say, bivariate convolution.
Yes, sir. Yes, sir.
Another question, as I've been working a little bit with bivariate fractional calculus, and in the definitions that you've considered here, you have a function of x1 minus t1 times a function of x2 minus t2. So in some way you have two separable functions. But yes, I've also looked at some cases where you define an integral operator with one single or double power series, where the x1 minus t1 and the x2 minus t2 are together. They're not separable as a product of two functions.
Okay.
Can your theory here also apply to operators defined in this way, like with a bivariate function instead of a product of two?
I don't know. It will be much harder, I think.
Okay.
If it is true, it will be much harder. But it's worth experimenting from you.
Okay, thank you.
My pleasure. Vasily.
Vasily.
George, very simple question, possibly stupid from an ignorant person.
No.
These are all very, nice result and approximation. I see it's very nice that you approximate all the derivatives together. But nevertheless, why do we really need it? Can you say, well, any concrete problem for which this approximation can help to solve it in some way or give some additional insight into problems? So some direct application.
Yeah, that's a good question. I don't know. Basically, I'm a computational analyst, pure mathematician. I'm not dealing with real life applications. I don't know. I wish something good comes out of it. But, in the very elementary case, when, the Caesar's problem, take a function f is increasing, you want the approximates also to be increasing, and this is achieved, okay? That you might think of possible real life applications. It's not hard to think that, you want to eliminate approximators and save time in calculations with a computer, whatever, and you want to consider only increasing approximators to approximate an increasing function as saving computer time. I don't know. I'm not, as I said, describing what I am.
Okay, okay, good. Thanks, George.
Thank you. Yes, sir.
Nikolai Leonenko.
Thank you, George, for an interesting talk. Well, I mean, usually Caputo derivatives and convolution time derivatives are related to subordinators. And in two-dimensional case, there is also theory of subordinators in probability theory. Can you say something about the relation between these convolution time derivatives and two-dimensional subordinators? There are some papers from Bardov-Nielsen and others.
Okay. In earlier work I've done recently, I consider Caputo type fractional calculus for stochastic processes. And I proved linear operator type approximation theory results, where you use simultaneously the left and right fractional derivatives. The expectation has the property to be exchanged and go inside the integral, and then you can have some probability related interpretations by exchanging the expectation with the integral, you know, with the Riemann integral. That's my experience with probability and fractional calculus. I don't know if it says something to you, but.
Well, I meant other things. I mean, there is a clear relation between in one-dimensional case, between the subordinators and stable subordinates and inverse to them, and fractional derivatives. Well, I mean, probably it's not nice. I mean, it's not easy to explain immediately, but people probably know this, some of people from this audience. And the question is, and also there is a theory of two-dimensional subordinated random fields. There are some people from Mexico, I think, Perez Hebrew, Bardov-Nielsen did such a theory. And the question is how this relates to, it should be, at least in separable case, it should be related, but of course, it's, well, anyway, that's probably far from the topic. Okay, thank you. Yeah.
Thank you, sir. Thank you.
Thank you. Are there further questions or comments? I don't see anyone. Then we thank the speaker again.
Thank you so much.
Thank you.
For coming late to listen to me. I'm in the United States. Here is 1 o'clock now. It's convenient time for me. I work also at night and I can get up at night, but I think I have better performance during that time. Okay, so I really thank you for coming late to listen to me.
It was our pleasure.
Thank you.
Thank you again.
Thank you.
Thank you.
Bye-bye.
Bye.
Thank you. Bye.
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 Thank you. Bye-bye.
Bye.
Bye.